All right, welcome back, everybody. Hope you can hear me here. I'm having a little bit of a technical problem. Okay, well, congratulations, you completed a week of chemistry. On to bigger and better things here. Okay, well, the game plan is this. Let me finish up chapter 1 and we jump into chapter 2. And then on Thursday, we'll get into chapter 3, a little bit of chapter 2. We do have scheduled next, I believe, let me double check. Yeah, the 11th for first exam, the 10th, I believe. Yep. That is, it depends on how well we do with the chapters. We can move that over a day or so, but we'll get to it. We'll know more on Thursday. Okay. All right. So, any questions? Everybody knows where to get their stuff, right? From the class, textbook, everything, right? No surprises down the road, right? Okay. Let me continue with the page that we ended up with, and we were on slide number 26. We had just finished talking about mixtures, compounds, and elements, okay, and how we depict those with diagrams. There's little spheres that represent atoms. Someone asked me one time, have we ever seen atoms? And the answer to that question is we have seen images of atoms. Back in the 80s, there was a technique done, an instrument, brand new instrument created by actually IBM, the ones that brought to your computer called STM, scanning tunneling microscopy. And with that particular instrument, you can actually, with a stylus, kind of like an old style record player, kind of go over atoms, and actually they got images of gold atoms. And so very resolution wasn't the best. The instrument has since gotten better. We're getting a little bit better with it, but we still, it did give us an image of atoms. Anyway, when we're talking about mixtures, there's a variety of different kinds of mixtures. Metals are a mixture, if you didn't know. Alloys, for example, steel by itself is very soft and does not function well as a metal to build buildings. So we have to mix it in with other material, carbon and other things, and end up with stainless steel, for example. The gold in your jewelry, again, not pure gold. It's mixed in with other material to give it a little strength so you can wear it, because pure gold is extremely soft. Sand, granite, tap water is a mixture because if you analyze the tap water, it comes in with all kinds of stuff in it. Yes, it's been cleaned up, it's been purified, but you got a lot of metal, you got a lot of ions and chlorides and minute organic material, so on and so forth. Gold is another. Air, is another example of a mixture because it's a mixture of gases. Pure material, obviously, if we take sodium chloride, here's a formula, NaCl, sodium chloride, pure, and we purify it. It's a pure material. Diamond. A diamond is a pure diamond. It's very rare to get a pure 100% diamond. But if you did, it would be made up of nothing but carbon. A lot of diamonds that are out there in the market have a little bit of impurity. In fact, that's what gives it a little bit of a color, if you will. Distilled water. Now, why distilled water is pure? Because you took tap water and you boiled it. Had a special instrument like a condenser, boiled it, let it condense, and you left all of the junk and all the other material in the container that you started to boil, and then you collected it. Sort of like an old-fashioned still to do alcohol. I don't know if you ever seen that TV program where moonshine. But that's one way. That's why all distilled water is. Water is being purified. And again, mercury by itself is a nice pure element. Now, how do we depict? Again, we're using diagrams to depict things. And on the far left, you can see that we have what represents an element, specifically a diatomic element. Remember, a diatomic element are those elements, there's only 7 of them, we'll get to those in a bit, that do not exist by themselves. They exist with another element. Hydrogen, for example, does not exist by itself here on Earth. So it's diatomic. So the formula for the element hydrogen is H subscript 2. And we depict those diatomic elements by putting together 2 spheres of the same color and the same size. So that represents an element, specifically a diatomic. Now, the compound, if you recall from definition, is a compound is made up of 2 or more different elements. Normally, one of the elements is the central element, and then everything else is bonded around the central atom. So you can see here, you got 2 different colors, a gray and a white color. It looks like the gray ones are bonded to the white one. And so that represents that the white one is the central atom, and the other moieties, whatever they may be, are bonded to the central atom. So you can see here, central atom. You can see here how we represent 2 diatomics. And so that both the first 2 examples of the element and the compound also represent a pure material, because there's nothing else in there. Now, the last diagram, you can see we have a mixture, because here we got this element here, a single element, could be anything. We got another one here. Obviously, it's different because of the color, a little bit darker. And then we have some kind of a compound here with the gray and the 2 white ones. It's some kind of a compound. It looks like a Mickey Mouse here. No, that's a good representation of water, for example, if you ever needed to represent water as a general diagram. So we got a mixture here of 2 different elements and a compound of some sort. Right now, these are diagrams. It's not depicting specific compounds, it's just in general. Okay. So what we have here is the question. We got the A through H, and the question is, all right, do we have an element? Do I have a compound, or do we have a mixture? What does A represent? Just like we did the previous one, definitely an element, and more specific, a diatomic element. Okay. B, it consists of 3 white ones and 1 dark one in the center. Okay, definitely by definition, a compound. Okay, and C, we have a clear one and a dark one, 2 different ones, obviously 2 different elements. Okay, let me get my 2 different elements here. So definitely we got a mixture of 2 different elements. Up to this point, it looks like we got a pure material for B and a pure material for A. Okay. The next one, again, D. So C is a mixture of an elements. D also represents a element, a single element. Okay, monatomic if you want to be technical about it, but it's just an atom all by itself, and it's pretty pure, because there's nothing else in there. So we got a element for D, and I jumped ahead, sorry. Again, here we have something with a clear and a dark sphere. And so that would represent some type of a compound, and there's nothing else in there. So E is an example of a compound. If we go to F, you can see that we have 2 compounds here, 2 different compounds, and then we have a diatomic element. So obviously we have a mixture here of 2 compounds and an element. And then G, we got a mixture again of an element of some sort and a compound. Again, you can see in that compound, the dark one is the central atom, and then the clear ones, the white ones, are 3 elements of some sort that are bonded around it. Okay. Then, where are we at? Finally, the last one is all clear and very ordered, and that certainly is a an element of some sort. And pretty much a solid, you can tell because all the spheres are nice and ordered, and that could represent an element in the solid phase. All right, so let's talk about the elements now. All right, now if you had a chance to look at the periodic table, I'm sure you're familiar with it. In my background is part of the periodic table, but the one we utilize, you would notice that each element does have a unique name, okay? And it has a symbol that normally is represented by a letter, a single capital letter, or two letters in which the first letter is capitalized and the second one is lowercase, okay? And then each one has a specific number. So very quickly, let me go to the periodic table that we utilize. And you can see here that, that each one here, there's 118 of them. Now, the ones down at the bottom, let me show you, because this one hasn't been totally been updated. But 115, 113, 115, 117, 118 have been created, and they officially now have a name. So we haven't got the updated periodic table at this point, but you can see here that each element has a letter, either a single letter, which is capitalized, or a double letter. If we look at B, which represents what we call boron. B is boron right here, okay? It has a number, a decimal number below it, which we're going to learn later on. That is what we call the atomic weight of that element, 10.81, okay? And then it has a number on top. Very important number, because that number represents the number of protons, the number of electrons. Okay, remember that the atoms consist of protons, neutrons, and electrons. And we're going to talk about how to calculate the number of neutrons, but just simply the element itself with its atomic number, which is a whole number that represents the number of protons and the number of electrons. The key aspect about that number is the proton defines what that element is, okay? We'll learn that we can lose electrons and neutrons all day long. Okay, but we still have a specific element number for, say, carbon. It's a number 6. That means it has 6 protons. And it has, in this case, we will learn that it's going to have 6 neutrons and 6 electrons. Okay, we'll get to that in a bit. But I can lose any of those 6 electrons or gain more electrons. The same with neutrons. I can lose more neutrons or gain them. But as long as I don't lose a proton, I still have carbon. The moment I lose a proton, now it becomes element number 5, which is totally different, boron, okay? If I gain a proton, I will become element number 7, which is nitrogen, okay? So the proton defines what the element is. Clear this. We'll go back. Okay, like I stated, first letter is capitalized. So hydrogen is H, carbon is C, but we do find some elements with second letters, and they are lowercase. So C lowercase a represents calcium. C lowercase o represents what we call cobalt. It's a heavy metal. Now, that's crucial and it's important, because if we were to inadvertently make the second letter capitalized, guess what? We have carbon monoxide, which is a compound, totally different, not an element. Okay, so you got to be careful in the way you're writing your symbols for your elements. Okay. Most of the symbols do have English names. So we got H for hydrogen, O for oxygen, He for helium. But then there's others that they're derived from Latin names. So for example, lead, its symbol is PB. It comes from plumbum, which means waterworks. Okay. Gold, the symbol for gold is AU, which comes from Latin meaning Orium, meaning golden dawn. Now, be familiar with the first 20 elements. Okay. And then on top of that, we're going to start with this batch. And then as we progress, we're going to throw more elements at you. And basically to remember their name and at least where to find them on the periodic table. So we got silver, which is Ag, Au, which is gold, Pb, which is lead, Br, which is bromine, I, which is iodine, and Hg, which is mercury. Now, with respect to 1 through 20, we'll go and run through that. Okay, you can see here that hydrogen is in the top left. So the way the periodic table runs is you start in the top left, and that is hydrogen right there, number 1. Okay, H. And then we go across the periodic table to He, number 2, which is helium. And then we go back to the left side, left column, first column, and we got Li, which is lithium. Then we got Be. Hold on a second. Which is a beryllium, number 5. We shoot across to number 5, which is B, which is boron, and then good old-fashioned carbon, very important element. Without carbon, we wouldn't be here. Okay. Which is C for carbon, and then its neighbor, number 7, is N for nitrogen. H is and number 8 is O for oxygen. Number 9 is F for fluorine, not to be confused. Here we're getting a little bit of number here. This morning, I'm sure you brushed your teeth and you probably had a fluoride, IDE, which is different from fluorine, INE. We'll learn the big important difference there, okay? And then number 10, Ne, which is neon. And then we go back to the far left, the first column, and we have natrium, otherwise AKA sodium, okay? Number 11. And then we have magnesium, Mg. And then again, we have we got to shoot all the way across the periodic table to number 13, and that is aluminum. And then good old Si, which is silicon. And then P for phosphorus, S for sulfur, Cl for chlorine, Ar for argon. And then finally go back again to number 19 to the first column. And then we go to number 19, K for potassium. And then C8 for calcium, okay? All right, so those are the first 20. And then with time, we're going to be learning a lot more. We're going to be working with zinc, which is Zn. We're going to be working with copper, which is Cu, nickel, Ni, cobalt. Basically, Br, which is bromine, is over here. And I, which is iodine, okay? We'll be learning all these. All right, so notice the trend here, if you haven't observed, that we start off in the far left and we shot across. And keep track of, let me clear this up a little bit. The other aspect, if you look at the columns, okay, if you look at the columns, they have a particular number in Roman numerals. And Roman numerals are the letter I. So we got IA, Roman numeral 1, Roman numeral 2A, we shoot across the 3A, and then IV, which is 4. Okay, Roman numeral 4, and then V, which is 5, VI, which is 6A, VII, which is 7A, and then finally VII, 3 I's A, which is 8. Okay, those numbers are very important. We're going to learn that that will tell us specifically how many electrons are on the outermost shell. We're going to learn that in the nucleus, we have the proton and the neutron, but then these crazy electrons are orbiting around the element. And that number is going to tell us how many of those are in the outermost shell. But we'll get to that. And again, we'll be using the periodic table to help us with that. You don't have to memorize it, just find this position. All right, so let's go back. All right, the physical states of these elements, of the 118 elements, okay? Now, this is at 25 degrees, because obviously if we were on the surface of the moon, everybody's a gas, okay? Everybody's an ion, actually. But when we talk about physical properties, we are talking about 25 degrees, which is approximately room temperature, 25 degrees Celsius, and at what we call 1 atmosphere of pressure. Right now, here, it is 1 atmosphere of pressure, okay? The physical properties can change if you decrease the atmospheric pressure or increase it. So under these conditions, there are only 2 elements of the 118 that are liquids. One is mercury, which is Ag, and the other one, which is bromine, okay, which is Br2. Also, Br2, notice it got the subscript. That's one of the diatomic elements. There's 7 of them. There's one right there. Now, all of the noble gases. Now, what exactly is noble gas? Well, what I got to do is go back to the periodic table. Okay, on column Roman numeral A, 8A, which is the one in the far right. There you go. Which is right here. Okay, they are called noble gases. And the reason they're called noble gases is because their outermost shell is full of electrons. And therefore, they have fulfilled a little law, a little rule that we have determined occurs, and that is the rule of 8, the octet. They have 8 electrons in the outermost shell, okay? And because of that, they are very unreactive. Now, helium, which is the first one, number 2, doesn't have 8. It has number 2, but everybody else has 8. And because of that magical 8 number, they're very unreactive, and they're what we call inert. Now, notice how many rows we have here. 1, 2, 3, 4, 5, 6, 7 rows. So there's 7 noble gases, okay, which are noble gases, okay, just like the name. So there's 7 there. Let me go back to where I was. And, oh, 7, 8, 9, 10, 11, 12. Hydrogen, nitrogen, oxygen, fluorine, and chlorine, plus the noble gases, which is group Roman numeral 8A, are all gases. So we got 12 elements that are gases. So we got 12 here. We got 2 that are liquids, okay? And so what about the rest? So far, we have how many? You got 14, right? There's 118 minus 14. And so we have 104. 104 are solids. Everybody else is a solid. And so once you know where the gases are at, and if you are given a element, any element, and just told, is this guy a solid, liquid, or gas? Okay. You should be able to determine their physical property at 25 degrees. Okay, so this little table demonstrates the gases and the metals, the solids, and the liquids. Okay, bromine is sitting right here, and mercury is right here. Those are the only two liquids. Okay, the ones in yellow are the gases. Here's the noble gases right here, noble gases right here. Okay, very near. And then we had hydrogen over here. We have nitrogen, oxygen, fluorine, and chlorine. Okay, and everybody else is a solid. And so if you're given, ask, okay, calcium right there, solid, liquid, gas, just knowing this position in our product table, you know its physical property. Okay, at 25 degrees. The diatomic elements. Of the 118 elements, we stated that there are 7 that are diatomic. They exist as pairs. Okay, so we use a little thing for you to help you out. Have no fear of ice cold beer or beverage, whatever works for you. So H represents hydrogen, N represents nitrogen, F represents fluorine, O represents oxygen, I is iodine, C is chlorine, not carbon, chlorine, and B is bromine. Now, why do you need to know this? Because sometimes we will get word reactions. In other words, you'll say something like sodium metal in the presence of chlorine reacts to give you sodium chloride. We have to take those words and convert them into a chemical reaction. Then we have to know the physical states. Chlorine is diatomic, so its formula is with the subscript 2. Its proper formula. Okay. All right, now we have 3 types of properties for these 118 elements. They're either a metal, okay, which normally one property of metals is conducting electricity, or non-metals, which generally means that they do not conduct electricity, and then semi-metals, which means they have properties of metals and non-metals, and some do conduct electricity. As an example, silicon, very important. Silicon, important for our computer chips. You know, given properly prepared, it will conduct electricity. So, but is a semi-metal. So non-metals are located on the far right, or we call the stair step. What do you mean by a stair step? Let's go back to the periodic table. I told you I'm referring to it quite a bit. Look at the stair step here, starting with number 5, boron. All right, you can see here, here's our stair step right here. And so if we, on the stair step, we have what we call metalloids. So to the right of the stair step are non-metals. To the left of the stair step are all the metals, okay? And that's important to know because that's going to define the type of compound that we will put together the elements to make. It will be either what we call ionic compound or covalent compound. There's only two types of compounds that we're going to utilize, and what defines it is whether it's a metal or a non-metal. You know, I've been using sodium chloride. We use that as an example. Sodium chloride. Okay. Sodium is a metal, and chloride is a nonmetal. So this becomes what we call an ionic compound. Carbon dioxide, carbon's a nonmetal, oxygen's a nonmetal. This makes a what we call a covalent compound. Okay, and which has specific properties. So that's why we need to know who's the metal and who's the nonmetal. We're not going to do much work with metalloids. It's going to be 99.9% of the work will be dealing with metals and nonmetals. Okay. And so here in blue are the nonmetals. Now, thing to remember, hydrogen's the very first one. It's in the far left. It's not a metal. Remember that. Okay, hydrogen is a nonmetal, and it's placed on the far left for a particular reason that we're going to learn about. But remember that it is a nonmetal. If you look at the metalloids, you start with boron, and it goes catty-corner across to silicon, and then it goes straight down to Ge, and then across to arsenic down to this direction, and then straight down again, and then across, and then straight down, and then across. Okay, and 117 is also the metalloid. So anything to the right, which you see in the color of pink there or red, is non-metal. All the blues are metals. Okay. And then the metalloids are as shown. So some of the properties of metals, well, in general, they're very shiny in appearance. You can take them and really smack them and spread them out. I used to work in my industry days with copper plates. We're about 1/4 inch, and the way they were made, you ended up with they were made in Europe, and I had an opportunity to see their operation. And they started off with a billet of copper, a chunk of copper, which was probably about 4 feet thick, and maybe it was about a 4 by 6 by 4 feet thick. And they took this big old chunk of metal, copper, and put it under presses and heat and squished it all the way down by rolling it back and forth until such time that we were down to a 1/4 inch thickness. And it was a big, gigantic plant that this occurred in. Also, they can be spread out. A lot of the copper, different sizes. They start off with a cylinder of fairly large size, and you can run it through what are called dies and force that copper metal to become smaller in diameter. So they have that property. Now, all the metals are solids except mercury. Mercury no longer used as much, but a lot of older homes have mercury switches for the air conditioning you turn off and the heater you switch off because it conducts electricity, and now it's all digital now, so not too much mercury being used. Density, remember that ratio, mass over volume, generally very high, very high. And mounting temperature, that temperature that it mounts, again, very high to get that thing to melt. They're very good conductors of heat and electricity, all right? Good conductors of heat and electricity. With respect to nonmetals, they generally have a dull appearance for those solid ones. And if they are solids, they tend to be brittle, not very hard at all. And a lot of them are gases. And their density is, in general, very usually low. Okay. And they melt at a very low temperature. Okay. And the fact that they're not conductors of heat, they're poor conductors, which actually makes them better insulators. Okay. All right. So there are some particular properties of metals and nonmetals. Okay, so be able to look at the periodic table to determine the name, at least for the ones we gave you, okay? Determine which ones are solid, liquid, or gas, okay, using that periodic table as a guide. and then be able to determine, well, which is a metal, which is a non-metal, and which are metalloids, based again by their position on the periodic table. Both of these color-coded periodic tables aid you in determining that. Okay, and then which ones are diatomic? There's only 7 of the 118. Okay. All right, so you know that solid, liquid, gas, we had 2 liquids, right? We had 12 gases and 104 solids. Whoa, okay. All right, so much for chapter 1. Okay, don't forget to do the assignments for that coming up. Any questions about chapter 1 before we proceed? We used to do the math skills. Yes, we'll be doing a little bit of math, but like I explained, if you can add, subtract, multiply, and divide, and there's some very small amount of algebra, you shouldn't have a problem. Okay. We used to do that beginning, but then it worked better. We decided to change it around and give you some chemistry because that's what this is all about, and then turn into the math skills. Why the math skills? Because eventually we're going to get to the point where we're going to be using these skills we're going to learn here to calculate in chemical reactions, okay? How to go from point A to point B with respect to chemical reactions. The math skills here are important because we're going to learn about significant figures. We're going to learn about which is exact numbers and which are not. And then, thing also to take away is we realize that when you do a calculation on a calculator, that a lot of times you end up with a number that's, 150 digits long. Well, you wouldn't represent, or you wouldn't present that data with 100 digits long because you're not that accurate with respect to your numbers. So we're going to learn about how to turn in the most accurate number that you have based on the least accurate measurement that you did. Okay. All right. So there's a read the chapter 2. Obviously, there's a lot of practical problems. I want to don't forget to do this. Anyway, a measurement. A measurement is any number with a unit, because you got to have a unit. Okay. Because if you just say a book weighs 8, it doesn't mean anything. 8 what? 8 ounces, 8 pounds, 8 tons. Without the units, that number is meaningless. Okay, so the other aspect, that every measurement has a degree of uncertainty. There's nothing out there that is 100% accurate in your measurement. Anything you weigh, the weight, there is a degree of uncertainty in that last number. If you measure the length, again, there's a degree of uncertainty. Okay. So, and what we end up doing is we end up estimating that last number. Okay. Now, what that means overall is this, that your answer should never be more accurate than the least accurate measurement that you did your data in, collected your data from. Okay. And what I mean by that is, yes, we can get a ruler and measure the length, or we can get a laser beam and measure the length, right? The laser beam is going to be a lot more accurate than the ruler. And so if we were going to take those 2 measurements, one measurement from the laser beam and one measurement from just a ruler, and multiply those 2 to give us an area, for example, our answer should be no more accurate than that ruler, because that is the least accurate measurement that we utilize in this measurement scheme. Okay, that's the thing to remember. Remember about all this. All right, so measurement in meters. Well, normally, again, we work in metrics, so we're using cm for centimeters, millimeters, meters, and km, kilometers. Okay. And in the sciences, yes, we know there's in English units, in inches and so forth, feet, but in the sciences, worldwide, the metric system is utilized. We will be using some of the English units to convert from metric to English as a practice to help us do calculations down the road with respect to chemical reactions. Okay, so we're not leaving the English units out of it right now. Obviously, rulers, have, depending, let's say we got the measuring ruler here, one's more accurate than the other. You can see that the white one is not very accurate because the brown one in the bottom has a lot more increments. So we could be a lot more accurate with the bottom measurement than we can with the white ruler, stands to reason. And so which ruler has more degree of uncertainty? Well, the white one does. Because why? We can only go maybe to the 1/10th position with the white ruler. Okay, so if for example, what do I mean by that? Let's say we were comparing this red line all the way down here. Okay, we want to measure that red line. So you can see that the white ruler, we're going to have to estimate maybe, I don't know, I can call that 4.5 from my perspective. Approximately 5.3 maybe. Okay. Whereas over here, the bottom one, I can go 4.321. So you can see the bottom ruler, we can go 2 decimal places compared to the top one, which is 1 decimal point. Okay, so that top one has a lot more degree of uncertainty just because of the measurement tool is a lot less accurate. Okay. All right. Now, when we deal with mass, again, remember we talked about that weight and mass kind of interchange a little bit. We use a balance. Now, the units that we utilize are mg for milligrams, kg for kilograms, and g for grams. Okay. Now, you can see the balances down at the bottom here. The analytical balance, if we were in the lab for reals, those of you who are doing the lab for reals, you'd be using the balance, not for reals, in person, I should say. The balance on the right is a lot more accurate. We can go to the 4th decimal place with the digital balance on the right, whereas the balance on the left is a little bit less accurate, maybe 2 decimal places at the most. Okay. So we talked about mass and weight, and have to talk about this, but weight is defined as is equal to mass times the gravity, and it depends on us. That gravity has a constant, I believe 9.8 meters per second square. So it would change with respect to what planet you're in. So, and that's why we interchange mass and weight, because at 170 pounds here on Earth, you're about 29 pounds on the moon, simply because the gravitational constant for the moon is a lot different from us. Volume. Okay, here's some pictures of some chemical instruments that we utilize in the lab. Glassware, plasticware, different size and shape. They all have a particular function. But the units we utilize are either liters, or it could be kiloliters, or most of the time, the majority of the time is ml, lowercase m. Note the L in liters is capitalized. The G for grams is lowercase, okay? But the volume is uppercase L. Syringes, you may be familiar with this, cc's. That's nothing more than cubic centimeter, okay? Cubic centimeter. And what we know is that 1 milliliter is equal to 1 cubic centimeter, or 1 cc. 1 cubic centimeter is a measurement of 1 centimeter times 1 centimeter times 1 centimeter. We end up with cubic centimeter. That's cm to the power 3, which is equivalent to 1 milliliter. All right, now this is for English units. We got the letter G, the big G here, right? just kind of help you out to remember, because I always had trouble. How many pints, quarts, and blah, blah, blah. Well, maybe this picture will help you out. The big G is a gallon, obviously. Within the big G, you have 4 Qs, which represent 4 quarts. So there are, in 1 gallon, 4 quarts. Now, within the quart, there are 2 Ps. So that tells you that there are 2 pints in 1 quart. And then finally, within the P, there are 2 little C's, which represent 2 cups. There are 2 cups in 1 pint. So I have these conversion factors. Now, a thing about these conversion factors to remember, okay, every one of these conversion factors is a ratio. Okay, remember I mentioned that about a ratio, like miles per hour, dollars per hour, and every ratio can be written in 1 or 2 ways. For example, if we look at 1 gallon, we can write 1 gallon in the numerator, and we can write 4 quarts in the denominator, write it as a ratio, okay? Or I can write it with 4 quarts in the numerator and 1 gallon in the denominator, okay? I write it in so every conversion factor we're going to utilize, just like if there was $50 per hour. I can write it with like this, or I could write it with 1 hour per $50, okay? Same thing with miles per hour, so on and so forth. So every factor here I can write in 1 or 2 ways. And I want to do that because I'm going to multiply these factors by a unit. So let's take the 1 gallon and 4 quarts. If the word problem comes out, I want to convert 10 quarts to the gallon. Well, I'm going to set it up with the gallon in the numerator because that's the units I'm looking for. And I'm going to take 10 quarts and I'm going to multiply that factor of 1 gallon over 4 quarts. Why? Look at that. My units cancel out when I do the multiplication, leaving me with the units of gallons, which is what I'm looking for in this particular example. Down the road, we're going to be talking about moles per, moles per gram or grams per mole, another ratio. Right now it looks a little foreign, but if you follow this technique, when we get into chemistry problems, I guarantee you, you'll set your problem up correctly. And we're going to end up doing with setting up at the most 3 of these conversion factors back to back, you know, keeping track of my units as we progress. 3 of these. All right. Just a side note there, because you'll see that in the next chapter. So these are factors to help you out with respect to English units. Now, in reading volumes, you may have pictures where you got to read the volumes. Two things to take away from this type of a diagram to read. 1, be aware of which direction your scale is going, okay? You can see if you look at the scale, this is the 0 point. So you are reading from bottom up, which means that if you read this number, this will be 20, I say how many units across? It's like 5. So this is like 21. So this is 21 right here, not the other way around, going down from here, thinking it's 24, 25 point, I don't know, 5. So make sure that you know where you're starting from, okay? The other aspect is this. Anytime there's a liquid in a cylinder, you form this convex shape. We call that the meniscus. The thing to remember is we read at the bottom of the meniscus to tell you the value. So you would read at the bottom of the meniscus, okay? And you can see here that you're going to guess as to the value of this number. So what would you say this measurement would be if you had to measure, give them a number for this value? The other aspect is this, you know, it's 21, right? It's at least 21. And you know, it's point something. It's at least point what? 21 point, if you split the difference, maybe 0.5, right? And that's as far as you can go because you're estimating the last point. You can't say 21.56 because you don't have more increments in there to make it a little more accurate. Yeah, so this would be a 21.5. If you see 21.4, that's fine. If you see 21.6, that's fine too, because that last number has a degree of uncertainty within 1/10 of a millimeter. So obviously, if you see 25, then that's wrong because you're not even near the ballpark. Okay. All right. Which brings us to the point what we call significant figures. All right. Now, this is where the challenging part comes into play, where these numbers. We know, for example, that the difference between, as we talked earlier, and we're going to talk about more here, if we look at a bathroom scale versus, say, a surgical scale, you know, or the examples we had, the scales that we weigh things, I can say one of them you can go up to four decimal places, the other one maybe 2 decimal places. Obviously, the one with the more accuracy has more digits in the number, right? Okay. Now, when we talk about significant, we talk about it's well, maybe let me do it this way, so there won't be no confusing here. Look at these two here. What would you guesstimate that first measurement to be? Who wants to take a shot at that? For the top ruler. What do you think I could write down if I needed to measure? Okay, what is your best guess? Who wants to take a shot at that? Go for it. How about this one right here? Oh. This one right here. If I had to write a number to give a measurement for that, what could you say? Okay, what we got? We got some answers. Let me pull it up. 21.2 sounds reasonable. Oh, I'm making a mess here with my 29.2 exactly. You know, because sorry about that. You can see that no, you're estimating that last number. So 29.2, that's as accurate as we can get to the 10th decimal place. Okay. And if we look at the bottom one, we can go one more decimal point. What would you guys think the bottom value would be a good value to input? 29.25 or 4? Would you guys agree on that? Yeah, 29.2 would be good here. And 29.2, we know 0.2 for sure because it's past the second increment. So that one's pretty sure. And the other one would be 0.5. Yeah, London, that seems reasonable. Okay, so you can see here that top one, we only went 1 decimal place. And the bottom one, we were able to go 2 decimal places. Okay, now, if for some reason we needed to take these two numbers and multiply them, our answer should have no more digits than the least accurate number, which would be that one. Yes, I know you can put those numbers in and you're going to get a slew of numbers in your calculator. And one tends to think, well, I'm going to present all these numbers, but that will be inaccurate and that will be incorrect because you're governed by the accuracy of the least accurate value that you have. Okay. So we talked about what are called significant digits, okay? Now, all numbers from 1 through 9 are significant. So in this particular, now when I say significant, I'm not talking about value, loss of value. We're just talking about significant with respect to using the correct number of digits in your calculations, okay? I wish they would have picked a different word than significant, because I think what most people would think, well, that number doesn't count. Well, it does count, okay, in the value, but it doesn't count when we have to present the correct number of digits as an answer. So all non-zeros are significant. So this number 4895.2 has 5 sig figs, okay? Leading zeros, okay? Leading zeros, and those numbers up front are not considered significant, because all they're doing is setting up the decimal place. Now, I'm going to have a simplified rule here for you, but we're going to go through the book's rules first. And then I'm going to show you a way you can just look at that number and very quickly determine whether it's significant or not. Okay? All right, so leading zeros do not count. And so this example, 0.0005454, okay, has 4 sig figs. Okay, captive zeros. Those are numbers that are in between two integers, like 3050. That first zero is captive between the 3 and the 5, so is considered significant, whereas the last zero is not significant. So 3050 has 3 sig figs. Okay. The second example, 0.00, well, those don't count because of rule number 2. They're leading zeros, so you're just holding your decimal point. But the second set of zeros are between two integers, between 2 and 1, and therefore do count as being significant, and therefore that number has 4 sig figs. Okay. And then when you got a trading zero that after a decimal point, they're considered significant. So 0.0880, the first 2 zeros are leading zeros because of rule number 2 do not count. But the second zero, the last zero after the 8, normally wouldn't count because of rule number 3. Okay, but there's a decimal point, therefore they do count as far as being accurate. So it has 3 sig figs for that example. Now, if you look at 28,500, there's only 3 sig figs because those 2 zeros are trailing zeros and there's no decimal point. And that's the rule to really look at. One, you look at any zero, because as you know, I just stated, numbers 1 through 9, they're significant, so it counts. But when you look at a zero, you ask yourself 2 questions, okay? And let's use the example right here. Let's use the example right here. Let's look at those 3 zeros. First question, ask, is there an integer in front of those zeros? The answer is yes, then maybe it's significant. The second question is there a decimal point in anywhere in that number? If the answer is yes, then those zeros count. If the answer is no for any of those 2 questions, those zeros don't count. So going to the numbers I circled, we got 0.00. Is there an integer in front of those numbers? And the answer is no, they don't count, they're not significant. Okay. Look at these zeros in here. Okay. Maybe we forgot that they're captive. Okay. But so we ask the question, is there an integer in front of those 2 zeros? And the answer is yes, there's a 2. Second question, is there a decimal point anywhere in that number? And the answer is yes. Therefore, those 2 zeros within the 2 and 1 count. See how that works? Let's try it on this one. On 28,500. First question, is there an integer in front of them? Yes, check off. Is there a decimal point anywhere in that number? No. So those zeros don't count, okay? The moment I stick a decimal point in there, all the zeros count. If I stick a decimal point right there, obviously I will have to put something like that. Okay, and you asked the question about these zeros. Yes, they are in front of an integer, which is a 5. And yes, there is a decimal point in that number. So therefore, all those zeros count. Therefore, I got 1, 2, 3, 4, 5, 6 sig figs in this example versus 3 in this example. Okay. All right. Well, let's try a couple. All right. Well, before we do that, now there are numbers that are exact. They're they're exact numbers. They're whole numbers, and therefore are not used to determine the number of significant digits. An exact number, when you talk about 14 people, there's 14 people exactly, not 14 and a half, not 13 point whatever. It's exact. Okay, so 14 would not, it's an exact number. 3 feet in a yard, 100 pennies, 100 cents in a dollar, 5, again, iPods or whatever you want to count, or 12 pack. All those are examples of exact numbers and therefore would not be a factor in determining the number of significant figures at the end of your calculation. Okay, so exact numbers are not involved in determining significant figures. Anything that is measured, you measure 7 inches, 200 pounds, 10 ounces, maybe liquid ounces, all those were measured using a tool. Okay, those guys are not exact and therefore would play a factor in determining the number of digits, significant digits in your answer. Okay, so be able to distinguish the two. So one way to remember is this: anything you measure that is a measurement is not exact and therefore would be a factor. All right. But before we do it, let's figure out how many sig figs. Anybody want to take a shot at the first one, 5.05? How many sig figs do we have there? 5.05. Ask the question. We know that the 5s count because they're 1 through 9, right? Exactly. It is 3. And if you forget about that, look at that 0. You forget about 0. The zeros are ones that always turn up like, I'm not sure. Ask the 2 questions. Is there an integer in front of that 0? Yes, there's a 5. Is there a decimal point in that 0? Yes, counts. If you forgot the rule about captive zeros, then those 2 questions will always help you out. 3. What about, that's correct. What about 1200? How many sig figs? Would you guys agree on 2? Yep, that's correct. Correct, Allison. Okay, next one. 0.02020. A little more complicated. Those 2 zeros are front are the leading zeros, so they wouldn't count. The zeros between the 2 are captive, so they will count. Okay. And then the last 0, it's a trailing 0. Ask the questions. There's an integer in front and there's a decimal point, so it counts. So we got 4 exactly. And you can ask that same question for all those 3 different sets of zeros, and you will come up with the correct answer again. Okay. If you forget about the rules, ask those 2 questions. 0.005. Okay. How many sig figs we got here? 1. Right. Remember, those zeros up front are leading zeros and don't count. That's correct, Allison. And then finally 50. Not finally 50. How many do we have? Just one. And then the moment we stick a decimal point and then we add zeros, guess what? We have now 4 sig figs in this example. Okay. This 1, 2, 3.45, they're all integers. Obviously, they're all going to count. Okay. And then 8.090, we got 3 sig figs. Okay. 3 sig figs. Now you might say, all right, well, what does this mean to me at this point? Mathematically, it means this. If I'm going to multiply or divide, let's say these two numbers, my answer should have no more than 2 sig figs because the 2 of the 1200 is the least accurate. Okay. The same is true here. If I was going to multiply or divide, this is only for multiply and divide between these two numbers, then my answer should only have 1 sig fig. Okay. So on and so forth. And that's why we need to learn that, these sig figs, because when we multiply and divide, and again, I repeat, only for multiplying and divide. Adding and subtracting is going to be a little bit different rule. But a simple rule. It's not complicated. Little flow chart to help you remember whether it's significant or not. Okay, again, asking the question about with respect to zeros, you know, because we know integers are significant. But before we can do the calculation, we gotta set up the rounding. How do we round the number up? Obviously, like I stated, you might do a calculation and up at 30 digits. Well, I need to learn how to round. And there's a simple rule. Okay. Yeah, we look at the number that we're going to round. Okay. Now, what's going to happen to that number is one or two things. That number that needs to be looked at to be rounded will either stay that value or go up to the next. And what determines that is its neighbor. Okay. Not what's down the street as far as its value. Let's say 1.23457. And we need to round right here in this position, at the 4. Let's continue. Well, we have to determine, is that 4 going to stay 4 or is it going to be kicked up to 5? To answer that, we look at the neighbor only. We don't care what's happening down here, okay? Don't care. Yes, I know if I take that 9, the next neighbor can go up to 9, and I go say 8. No, you're just propagating here. You simply look to the immediate neighbor and you ask these two questions. If the immediate neighbor is less than 5, then we don't round it up. If that immediate neighbor is greater or equal to 5, then we round it up. So this number would become 12.35 because its neighbor is following this rule. Okay. If that number was 12.343678.9, okay, and we're looking at that 4, and then we would simply be 12.34, okay, because the neighbor is less than 5. All right. So what do we mean by changing the magnitude? I think a rule to remember is this I'm making up these numbers very quickly. Okay, if I need to round up at the 4 here, then it's straightforward. We look at the neighbor and then we end up with keeping that 4 as 4, right? Okay, and we drop everything after the decimal point. But what if it's before the decimal point? What if we were trying to round up at this 4? Okay, and we're before the decimal point. So we look at the neighbor here and we see it's greater than 5. So that 4 now becomes a 5. So it goes 12, 0, 5. What happens is anything before the decimal point becomes 0. We drop anything after the decimal point. And so that number becomes 12050. Okay. If we drop that 5, guess what? We change the magnitude. Now, because look at the number, we're in the 12,000 range. And by dropping that 0 because of the 5, we go to the 1200. We have changed the magnitude. You don't want to change the magnitude. So anytime you get ready to round up numbers with you have to determine the numbers in front of the decimal point, look at your magnitude of the number that you have, so you can still maintain the same magnitude. Okay. And so if we're rounding up to 1 sig fig, 5400, that's the first number, 1 7 digit. We look at the neighbor and it's less than 5, so that 4 becomes 0. Then that number becomes 5,000. Okay, not 5. Okay, because if you drop those zeros, you change the value, you change the magnitude. Which would you rather have? $5,000? What if this was money? Or $5? Okay, it's a big difference there, right? Okay, so be aware of the magnitude of the number that you're working with. When you're working with numbers before the decimal point. After the decimal point doesn't make a difference because you can drop them all off. You don't change the magnitude. Okay, for example, round these numbers to 3 sig figs. So what you do to determine the 3 sig figs, you start from left and count 3 positions to the right. And that's where it is. Okay, 1.8374. We got to go to the 3 significant figure digit or position. So you do that from left to right, and that's number 3. We look at the neighbor. It's a 7. Using the rounding rules, it's greater than equal than 5. Therefore, that 3 becomes 4. So we round it up to 1.84. Don't forget your units, centimeters. Okay. Another number. We're still maintaining the 3 significant digit position from left to right. That means we're going to truncate it at the 6. Okay. So then we look at the neighbor, okay, which is a 2, which means that 6 remains a 6. Also note the magnitude. You are at $7,000 magnitude. That means that 2, you cannot drop it off. You have to replace that with a 0, because if you don't, you change the magnitude. The numbers after the decimal point, you can drop. Don't make a difference. You don't do anything to the magnitude. So these guys can go away, and that 2 becomes a 0. Okay. And your answer is 7160, not 716. Okay. There's a big difference. $7,160 versus $716. All right. Here, same position. Remember, the zeros are leading zeros, so they don't count. So we start at the 1 and count three positions to the right. That means that 1. We look at the neighbor. It's less than 5, so we can drop the 1, the 5, and the 4. Now, you might think, well, wait a minute. How come you didn't replace that with zeros? Well, look where you're at. You're at the right of the decimal point. Remember that, you're to the right. So I can drop any numbers to the right of the decimal point. If you replace them with zeros, what have you done here by replacing the 154 with 3 zeros? Anybody tell me? If you replace the 154, what have you done? What have you done by replacing, thinking that you're going to change the magnitude? But remember, we are to the right of the decimal point, so we can drop any numbers other than the leading zeros, because that changes the magnitude. But any numbers after the 3rd decimal digit, the 3rd significant number digit, it can drop. And if you put zeros back in, what have you done? Think about it. How many sig figs does this one have? 3 sig figs. That's what the problem asks. And what have you done by adding 2 zeros? How many sig figs do I have here?
6.
6, exactly. Thank you. You have created 3 more sig figs, which is counter to what the problem said to do. You want to be in the 3 sig fig position. Okay. All right. So remember, before the decimal point, you replace the zeros. After the decimal point, you dump them off. You don't want to add zeros. Okay, let's do one more and then we'll just finish this slide. We'll call it. The 9 is the 3 sig significant figure position. We look at the neighbor. The 2 is less than 5. So therefore the 2 becomes 0 and along with the 5. Because remember, you're at the 24,000 mark here. And so that is our number, 24,900. Okay. Key points. Drop numbers after the decimal point. Don't replace with zeros. Okay. And numbers before the decimal point, replace with zeros. Otherwise, you change the magnitude, like in the case of number 2 there in white. Okay. Which slide? Let's see. 19. All right. Well, let us stop it here.